Okay, so hello everyone. Our starting point is pack learning, where the goal of the learner is to return an hypothesis which is close to the correct one, to the correct hypothesis with high probability. But in real life, learning algorithms have their limitations. So one extensively investigated constraint is on running time. But another constraint that started gaining popularity in the last few years is bound on the memory. So let's see what is a bounded memory algorithm. So if our algorithm has b bits, the learner can be in at most 2 to the b memory states. The learning algorithm gets inputs and then changes the memory states accordingly. This can be represented in a layered graph. So the algorithm begins in some memory state, and then it gets some labeled examples, and then it transforms to different memory states. In the ith layer, we have all the possible memory states after viewing I examples. In the final hypothesis, in the final layer, we have the output of the hypothesis, which is supposed to be close to the correct one. So this is a bounded memory algorithm. What we want to know is how many examples are needed given that the algorithm has at most some bound on the memory state. So let's start with some simple observations. First, if we have less than age memory states or less than log age bits, then we cannot represent all the hypotheses in memory. So if all the hypotheses are far apart, we just can't learn this class. So we must have at least age memory states. We also must use at least log age examples, because if we have an hypothesis class with the maximal VC dimension log age, then we must use at least log age examples. Okay, now let's move on to more positive observations. So the first observation is that we can have an algorithm with age memory states. What is this algorithm? Start with arbitrarily order all the hypotheses. Then check whether the first hypothesis is the correct one. It's an easy task to check whether an hypothesis is close to being correct simply by getting a few labeled examples. If it's not correct, move on to the second hypothesis class and continue in this way until you reach the correct hypothesis. Okay, so if we have more memory states, then clearly we can use the same algorithm. And now let's move on to another simple algorithm, the ERM algorithm. This algorithm simply returns an hypothesis that is consistent with all the examples seen so far. So at the beginning, all the hypotheses are possible. After seeing one example, the version space, the set of all hypotheses that are consistent with the current example, is smaller set. And then it's getting smaller and smaller until after log age examples, we get an hypothesis which is close to being correct. So this algorithm is great. It has at most log age examples. But the number of memory states that it uses is quite high, because it basically needs to remember all the examples that it's seen so far. And of course, if we have more memory states, this can be done. The immediate question is, what's going on in here, in this white square? So this question was first raised in a private communication by Rachameh, and then it was raised more publicly by a group from Stanford a few years ago, and they asked whether one have less than age log x examples, memory states, how many labeled example one needs. The group from Stanford asked it for one specific class, photo parties. And Ran Raz answered this question and gave a very strong long one for the class of parties. But this was for one class, and his techniques were fit for this class. What we wanted to know is whether this kind of claim can hold for general class. So this is what we wanted to know. And in order to give you our answer, we first need to look at class in a different way, via graphs. So how can you review a class through graph? We will think about it as a bipartite graph. On one side, we will have all the hypotheses. On the other side, we will have all the labeled example. And there is an edge between an hypothesis and a labeled example if they are consistent. This view of classes as graph enables us to use tools from graph theory in learning theory. And specifically, we will use the tool of random graphs. So let me just tell you what is mixing or random graph means. So we want to check how close a graph is to being random. And how can we check it? What we want is that for any large sets S and T, the number of edges between S and T, we want it to be close to what we expect. And what is the expected number of edges between S and T? Is the maximum possible edges between S and T, which is S times T, times the probability that there is an edge between S and T. The probability there is an edge in the graph is called the density, and it's the fraction of edges in the graph. But of course, we don't expect both of them to be equal. We allow some deviation, and the parameter d controls this deviation. If d is large, then this deviation is large, and the graph is far from being random. If d is small on the other end, then we say that the graph is close to being random. Let's look at a few examples. Sorry about that. Okay, so first, parities is square x mixing, which means it's very close to being mixing. If you take a random bipartite graph, it's also going to be close to mixing. This is known in random graph theory and easily proved using Chernoff and union bound. Okay, now I can present you our theorem. So this is our theorem. If the hypothesis graph is square x mixing, and the bound on the memory is h to the power of 1 to 5, then we must use polynomial number of examples. Remember that the ERM algorithm used only log h example. So there is an exponential increase in the number of examples that we use. In this case, we simply say that the algorithm, this class cannot be learned with bounded memory. So what we have here is some combinatorial sufficient condition for unlearnability with bounded memory. Kind of remind us the condition VC dimension equal to infinity, which is some combinatorial condition for proving unlearnability. And I think that the main contribution of this work is a new framework for proving lower bounds. That is very natural and flexible, as you will soon see. Okay, after we proved this result, we were able, with new ideas, improve this bound to a much better one. And this is our result. So let's look what we have so far in the table. So this is our table. Most of the white square is impossible. This result was proved independently by Raz, and he used the algebraic notion of mixing, which is the singular values. And note that there is still some white over here, so this question is still not closed, and we don't know optimal bounds for every class. Okay, now I want to show you a bit of our framework. The main concept that we use is certainty. We want to know how certain a memory is in its answer. Notice that each memory state defines some distribution over the hypothesis, which states what is the probability that some hypothesis is the correct one, given that we have reached this memory state. So if the memory is very certain, then this distribution is going to be concentrated on some hypothesis. And if this memory is uncertain, this distribution is going to be uniform over all the hypotheses. So if we want to know how certain a memory state is, what we can do is use some deviation measure from this distribution to the uniform one. So we use the L2 square, and this is our definition for certainty. And we can also define certainty of the entire algorithm, which is the certainty of all the memories, the average certainty. So this is how much our algorithm is certain of its answer. Okay, so now the outline of the proof. At the beginning, the algorithm doesn't know anything, so the certainty is very small. At the end, after the algorithm learned, the certainty must be very high, some constant. What we will prove is that if the memory is bounded, the certainty cannot increase by much at each step. This immediately means that we must use many examples if the algorithm is bounded. So now I will focus on the third step. But of course I can't tell you all the details because it's 51 pages and I only have 20 minutes. But here's the intuition. When we are given a new example, the algorithm, the learner, can use one of two different strategies. The first strategy is to remember only a little bit about the example that he got. But since the class is mixing, it won't help him to increase the certainty by much. The other strategy is to remember the example in detail. But since the memory is bounded, it must erase previous knowledge. And this is the reason why, in this case, also the certainty of the algorithm will not increase by much. What we prove in the paper is that any algorithm can basically be decomposed into one of these, into two these steps. Okay, so now the framework in general. So we talked about the certainty, which is a way to measure how certain a memory and algorithm is in its answer. We defined the concept of a hypothesis graph, which is a way to view a class as a graph. We defined a random property for it. And we showed that any algorithm can be decomposed into two of these different strategies. I didn't have time to present another two very important concepts. The first, representative labeled example, which means that if we take a memory which is uncertain, then for most examples, the label cannot be guessed. Another very important concept is knowledge graph. We were able to define yet another bipartite graph that capture exactly the knowledge of the algorithm at each step. We then needed to define a random property for this that we called K-expander. So these are the main concepts of the framework. Hopefully you feel it's natural and flexible and can be used in other proofs. So applications and open problems. Since we said that most classes are mixing, this immediately implies that most classes cannot be learned with bounded memory, which was quite surprising for me at least. Another implication we have from a theorem from random graph theory is that if the class contains hypotheses that are far apart, which we call error-correcting codes, then again, this graph cannot be learned with the bounded memory. The immediate type of question is to prove other application of this work. We proved that mixing is sufficient for unlearnability with bounded memory. But what about necessary? And another open question is that I would like to see something similar to the fundamental theorem of statistical learning also in the bounded memory case. And that's it. Thank you for listening. And I'm looking for a postdoc for next year, so if you're interested in what I'm doing, talk to me.
So, questions?
So, can you say something about the memory requirements for like learning half space, for example? Can you use some?
For half spaces, I guess that the it's not going to be a good mixing graph, since we know it can be solved with bounded memory, like the perceptor.
Well, first of all, we can maybe, let's say the margin can be small, but still there are the parameters of dimension. And let's say we don't assume anything on the margin. Can you do it with, can you prove that it's more than d, if you're in d dimensions, it's more than d? All the elements that we know will require at least d squared memory. Mm-hmm. And can you analyze it through this framework?
It's a great open question. I'll think about it.
Do you get lower bounds for learning with respect to which distribution?
I'm thinking about the uniform one.
Over the right side of your graph.
Yeah, exactly.
So Michal, I guess anything that's SQ learnable would be learnable with bounded memory?
It's also a very good question.
No, that was somewhat. Well, there are some upper bounds of this form in that Valley and state. You can get low memory for well, of course, it depends on the class, but you can get something like log of the hypothesis class
Times some accuracy. Sure. Okay.
So in this little for parentheses, you can rederive low memory. Memory lower bound implies success.
More questions?